Okay. Okay, for this subject, slope stability analysis, for today, for this lecture session, okay, I will discuss on the slope failure, okay, type of slope, okay, causes of failure and type of failure. Okay. So try to finish within 2 hours. Okay. So we will have a break for every 1 hour. Okay. So at 4 o'clock, okay, we will continue for the infinite slope. Okay. So I will give a lecture for 1 hour and then we may do some exercise for 1 hour. So in total 4 hours for today class. Okay, a little bit background on me. Okay. So my name is Ahmad Safwan. I've graduated from the Sheffield University. Okay. So this is my, sorry. Okay, this is my former supervisor, Dr. Hurt. This is my examiner, Dr. Craig from University of Manchester. Dr. Cripps, the internal examiner. And this is my second supervisor, Dr. Black. Okay, so these photo sessions was taken up right after my Viva session or oral examinations, okay, in 2011. Okay, is it a very tired session, okay, and very tough, where I need to defend for my four years work within 4 hours, okay, page by page, okay. So yeah, Alhamdulillah, at the last I have graduated, okay, because my supervisor, this is my former supervisor, okay? So very English person. So I need to work from 8 to 5 every day. Okay? So sometimes I need to back at 3 a.m. in the morning and then come back at 8 a.m. on the same day. Okay. Okay. So this is my family. The oldest one is the eldest one is now 15 years old. Okay. So this is the second one, now is 13 years old. Okay. At that time, my wife pregnant for the third kids, a daughter. So now is 11 years old. And I have another one, 5 years old. Okay. So the photo is taken when I just submitted my thesis. Okay. Because it's very we could not take for a photo, especially for the university signage, unless we feel confident that we can pass the oral examinations or we have submit the thesis. Okay, so that's why I capture this moment, okay, and then because I have submitted my thesis. Okay. So the University of Sheffield is located around 2 hours from Manchester, because I guess most of you are not, Sheffield University is not very familiar with some of Malaysian. Okay. So if we mention on Manchester, okay, actually Manchester United, I guess all the Malaysian know where is Manchester located. So Manchester is, we call as a Midland, while Sheffield we call as a East Midland. Okay, on the same longitude, but it's towards to Malaysia or toward to the east. Okay. So this is my thesis, okay, where I work on behavior of weak soil reinforced with soil columns formed by the deep mixing methods. It is a part of ground improvement method, okay, where we mix soil and cement or any stabilizer, lime, okay, for example, okay, and then with the original soil, okay, to improve the or to treat the ground. Okay, because for the soft soil, okay, uh, the the strength is very low. Okay, so that's why we improve it by using this soil seaming column approach. Okay, so I'm using this kind of 1G or small scale physical modeling. Okay, then the equipment using what we call it as a strain control system. Okay, so whereby we load we apply apply a load, okay, on the treated soil, and then at the same time we recorded the deformation and also the pressure or the load applied on the footing. Okay, at the same time a camera was used to capture for the movement or the deformation of the soil. Okay, so this is the image, okay, of the typical failure mechanism. Okay, actually this typical failure mechanism has been discussed by Prandtl in 1928, if I'm not mistaken. Okay, almost 100 years. So this is the most accurate method during my PhD, okay, whereby we can observe, okay, for the movement of the vector in millimeter or in micrometer actually. Okay. Previously, people use what we call as a noodle, for example, a Maggi, like a Maggi, a noodle, okay, to look on this failure mechanism to capture it, okay. But at that time, during my PhD, so I'm using the particle image velocimetry algorithm developed by David White from Cambridge. So by using this algorithm, so I can produce this kind of failure mechanism. Okay. So then this is the dissections, okay, for to monitor to observe for the column failure modes. Okay. This is for the end bearing type of soil seaming columns, and I also carry out for the floating type of columns. Okay. So that is a little bit of my my PhD study. Okay. Okay. Now we discuss on the slope failure. Okay. So simple definitions. Okay, where the slope failure is the movement of mass on slope. Okay, so we can categorize either it is a fall types, slides, or flows. Okay, so I guess last month we heard about the debris flow, okay, which is happened in Yan Kedah. Okay. So this is the type of soil movement, okay, where we can consider as a soil failure, slope failure. Okay. So some of the researcher has categorized it under two type of slope failure, okay, which is the first one is the landslide. Okay. It involves an extensive area. Okay. It covers a very large area, mild slopes, which is less than 20 degree. Okay. So the movement is slow and gradual. Okay. So another one is the slope failure. Okay. Where only localized area, which is limited area, while the slope little bit steep compared to the landslide event. Okay, so it's greater than 20 degree. So the movement is fast, okay, sometimes with no sign. Okay, normally it is happen due to the influence of rainfall, okay, which is infiltrate inside the slope surface or slope structure. Okay. So for both cases, okay, either we can what we call as observe by using a general or global approach. Okay, so now we have what we call as what we remote sensing approach. Okay, then we can monitor or we can observe the movement. Okay, or we want to carry out for a very localized investigation. Okay, then we use what we call as a limit equilibrium software or numerical or a finite element software, okay, to determine the factor safety of this slope. Okay. So the stability of a slope should be evaluated when slope movement due to additional load or loss of strength is identified to cause problems. Okay. So the way that we evaluate, normally for as an engineer, we use the term of factor of safety. Okay, where we need to find what is the driving force and also what is the resisting force. So all of this calculation is based on the soil property itself. Okay, so if we want to make a very thorough analysis, okay, maybe we need to include, okay, the rainfall intensity, okay, in the study. Okay, or if you want to go more deeply, so we can use the unsaturated soil mechanics approach. Okay, so that is the way how we identify or determine the factor safety for a localized area. Okay. Okay, this is a type of slope failure, okay, where we have a fall, okay, toppling, spreading, sliding, and flowing. Okay. So in our topic, we only could discuss on the sliding, okay, whereby we can determine the factor safety, okay, based on the sliding event. Okay, and also on the spreading, we use um, the infinite slope approach, okay, to identify the factor safety of this kind of potential failure. Okay. While toppling is a common type of failure for the rock slope, okay, and also for the fall, okay, but we may not discuss in this topic because this is more related to the rock mechanics. And also for the flowing, okay, I will not discuss in this topic. Okay. So it's more related to hydraulic or hydrologist field. Okay. So we may discuss on the spreading in terms of due to the failure is related to the infinite slope. Okay. While for the sliding, okay, it is due to the failures normally happen on a finite slope. Okay. So fall, okay, this is the detachment of soil or a rock fragment that fall down the slope. Topple, this is a forward rotations of a soil or rock mass about and axis below the center of gravity of mass being displaced. Okay, slide, this is a downward movement of a soil mass occurring on the structure of rupture or on the surface of rupture. Okay. Widespread, this is the form of slide by translation. It's caused by a sudden movement of water, bearing seams of sand or silt overlain by clay or loaded by fill. Okay, normally for the spread, when we analyze the infinite slope, okay, we should imagine there will be a failure surface, okay, in order to calculate for the factor safety value. Okay, the same goes with the slide. Okay, so we need to um, produce the surface of rupture, okay, in the analysis, okay, whereby we can determine the factor safety, okay, by using either a total stress or effective stress approach. Okay. While flow is a downward movement of a solid mass similar to a viscous fluid. Okay. So this is due to the normally happen in the forest area, okay, like what happened in Yan previously. Okay. Actually, I have involved, okay, in this debris flow problems, okay, whereby the government, okay, want to build what we call it as a sabo dam or sabo dam is a term in Japan. Okay. While normally in Hong Kong they call it as a check dam. Okay. So it can minimize the effect from this debris flow. Okay. Because this dam will cater or will sustain for any debris movement, or will catch or capture the debris movement, okay, before it meets for any residence area downwards the hill. Okay. So type of slope, we have a natural slope and man-made slope. Okay. For natural slope, it is a long-term process, okay, and a short-term process. But normally, short-term is also referred to a very long in relative for us as a human being. Okay, might be it's more than 100,000 years. Okay, and the formation of field and valley, okay, means that the natural slope is what existing landscape that we have that have a slope. Okay, while for the man-made slope, okay, we do something or we do excavated on the natural slope, okay, due to development. Okay, for example, for this area, for this figure, okay, so this is the existing slope. Okay, the dash line, the green dash line. Okay, so then they excavate it. Okay, for example, to make a highway or to make a road. Okay, then we consider as a man-made slope, which is the excavated slope. Okay, so we have disturbed the original slope or the natural slope, okay, due to the need of development. Okay, then we have another slope we call as slope of embankment and earth dam. Okay, so this is a man-made slope. Okay, for natural slope, okay, when we want to analyze it, okay, we may use the factor safety. The factor safety should greater than 1.2 to 1.4. Okay, while for the man-made slope, the factor safety should greater than 1.5 to ensure the stability of the slopes. Okay. So this is slope of embankment, while this is slope for the earth dam. Okay. So for this type of slope, so we need to check for this stability. Okay. And at the same time, we need also to check the bearing capacity of this embankment structure. Okay. So for a typical slope degree, okay, so we need to make sure that the degree of the slope that we propose is 1 vertical to 2 horizontal. Okay, so the slope degree will be 26 degree or 26 degree. Okay, so if more than that, okay, so it has a potential to decrease the factor safety. Okay. So for the embankment construction, we need to make sure that the compaction of this soil should greater than 95 degree. 95%. It should similar to 95% of the maximum dry density from the compaction test. Okay, so this is the earth dam. So the construction of earth dam also should also meet the same specification with the embankment, but we need to carry out for the seepage analysis due to the reservoir or due to the water is located a little bit below on the top of the slope. Okay, so in that case, we need to run for the seepage analysis. Okay. But normally we can use whatever software, for example, SIPW, combined with the slope W, okay, to carry out for the analysis of this type of earth dam. Okay. Okay, for the slope terminology, okay, so we have a height, toe, slope ratio, okay, terrace. Okay, I guess this is the US term. Okay, for the UK term, they call it as a berm. Okay, so we have a surface or face, top, and surcharge. Okay, so this is the common slope terminology. Okay, so for the soil slope, okay, it is suggested to use 2:1. Is that refer to horizontal to vertical? Okay, so it's not very common to use 1:1. Okay, because actually a rule of thumb, okay, if the internal friction angle of phi is greater than the degree of the slope, okay, so we can consider the slope is in a stable condition. We discuss later on, okay, when we go through for the exam for another discussion. Okay, so there is simple simple way, okay, to ensure the stability of the slope. So that's why by using 2:1, so means that the degree is 26. Okay, so normally for soil, okay, under the effective unit weight, so effective friction angle, so the degree is around 28 to 30 or 32, okay, 33 something. So that's why if 1/1, so the ratio is 45. Okay? So it's not very safe, okay, to use 1/1. Okay? Some situation they use 1.5 to 1. Okay, so the slope is around 30 something. Okay. So for every 6 meter height of the slope, need to construct for a berm or terrace. Okay, with the width of the terrace or berm around 2 meter. Okay, to allow for any machinery to park or to put on the terrace or on the berm. Okay. So for the surcharge, especially if we want to construct for any building on the top of the slope, so we need to make sure that it is not within the rupture failure zone. Okay. So normally it should have a distance, okay, up to 2 height of the slope, okay, to ensure that this surcharge is not considered as a additional loads on the slope structure during the analysis. Okay. Okay. So principle of slope stability analysis. So sliding will occur if the shear stress developed exceeds the corresponding shear resistance of the soil. In this case, failure is assumed at a certain plane. Okay. So this is simple analogy, okay, where we assume this is a block of soil. Okay. So this block has its own width or mass. Okay. So from this plane, failure plane, okay, so it has a certain degree. So in this case, it considered as a alpha. Okay, alpha is the angle of the slope. Okay. So the W sine alpha is the driving force, while RS is the resistance force. So for example, if RS is greater than W sine alpha, so definitely the factor safety is greater than 1. If W sine alpha is equal to RS, so definitely is the factor safety is equal to 1. Okay. So in that case, to ensure that the slope are in a stable condition, the ratio between the RS and W sine alpha should greater than 1.25 to 1.4 for natural slope and 1.5 for the man-made slope. Okay. So in that case, okay, we need to identify what is the RS value and also what is the W sine alpha value. Okay. So in from this analogy, okay, so several researchers come up with their own approach, okay, to come up with their own equation, okay, to determine the factor safety value. Okay, so we go through in detail, okay, to discuss on this analogy of the block, a block of soil located on a sloping plane. Okay, so we just, okay, this is the unconsolidated sediment. Okay, while this is another surface of sandstone. Okay, so we need to know what hold the sediment in place, okay, and then what pull it down. Okay, so what holds may contribute to the resisting force, and what pull may contribute to the driving force. Okay. So then we draw what we call as a block, as a similar from the previous discussion. Okay, then we have this kind of degree of the slope. Okay, which is a theta. The W is the weight of the block towards the gravity. Okay, so what hold the block on the failure plane? Okay, actually is we call it as a normal force. Okay, it is a perpendicular to the failure plane. And what pull the uh, the the block down, okay, is due to a parallel force, okay, with the failure plane. Okay. So this is the simple figure, okay, to explain on this slope stability analysis principle. Okay, the weight is concentrated at the center of the block. So this is the slope angle. Okay, we focus on the W. So the weight always point straight down, okay, due to the gravity force. Okay. So then we resolve it by finding the FP, okay. So component of parallel to the slope, okay, and then there should be another one we call as a Fn. Okay, now we focus first on the FP. Okay. So by using the trigonometry, okay, then we have here theta. Okay. So I still remember when I sit for my SPM in 1998, okay, or during the PMR in 1996, okay. So I guess we learn on the trigonometry subject, okay, where we need to identify the sin, cos, and also the tangent. Okay. But I still remember until now, okay, for example, to find for the sin, okay, cos and tangent. So for example, for sin, this is a Malay term. This is the tentang, and this is hypotenuse. Okay, this is cos. This is CC adjacent. Well, this is the hypotenuse. Okay, and for the tangent, this is opposite. Well, this is the sorry. This is the adjacent. Okay. So my teacher teach me, okay, a simple wording. Saya tak hafal, kalau saya hafal tentu tak susah. Okay. So until now I remember it and use it, okay, for the trigonometry. Okay. So then by knowing this knowing this data, so we can get what would be the value for the W, which is parallel to the failure plane. Okay. So then W times sine theta. Okay. Because this is the theta, this is the theta. So if this is the FP, okay, so W, sorry, so this is the W and W. Okay. So sine theta equal to FP over W. Okay, then on FP is equal to W sine theta. Okay. Opposite over hypotenuse. Okay. So the force parallel to the inclined plane FP is what pull it down the slope. Okay. So that is the FP value, okay, which is the parallel. So P is parallel. Okay. So we consider this is as a driving force. Okay. Okay. So this is another extra explanation. Okay. Where small angle, definitely there will be a small pulling force. Okay. And if the angle is large, so it can provide a large pulling force, okay, for the FP. Okay. So okay, that is for FP. Okay. Okay, now we go for the what we call as for the FN. Okay, slope mechanics and material strength. Okay, so this is contribute to the FN. Okay, so for the FN is W times cos theta. Okay, which is the adjacent of hypotenuse. So the component of weight normal or perpendicular to the slope, which is the N normal, okay, normal force acting on the failure plane. Okay, so the normal force is what contribute to a force that resists movement down the slope. Okay, it is a part control. For example, it's a part control the material strength. Okay. So, okay, this is just a simple analogy. Okay, what happen if we try to pull, okay, a block on a zero on the flat or horizontal surface. Okay, then the friction force will contribute, okay, to the resisting during the pulling process. Okay. So the Fn, okay, times coefficients of friction. Okay, so this is try to relate to what we call as to the properties of the material. Okay. So the effective the coefficient of friction quantifies the degree of roughness, okay, between the two surface, okay, which is the bottom of the block and horizontal surface. But in soil, okay, so this is contribute either from the cohesions and also from the frictions. Okay, because in soil we have C and also Phi. But for this kind of example, okay, so it's related to the roughness between both surface, okay, from the bottom of the block and also from the horizontal surface. Okay. So this is just example. Okay, if both of the block and surface is moved, okay, so definitely it has a low coefficient of friction. Okay, while if both of the block and also the surface is rough, so it may have a high coefficient of frictions. Okay. So the coefficient of friction change with geologic material. Okay, so this is example for a friction that has in a clay, okay, which is 0.1 to 0.3, okay, and sand 0.4 to 0.8, okay, and broken rock, which is 0.5 to 0.9. So this is not a friction angle. Normally friction angle we use in degree. Okay, okay. So it is not a friction angle. It might be they calculate and they determine, okay, using the surface roughness device. Okay. So normally for a mechanical researcher, okay, they use the surface roughness to determine the roughness of the surface. Okay. So the Greek symbol nu is usually used for coefficient of friction. Okay. So the coefficient of friction also controlled by mineralogy. Okay, quartz is strong, olivine is not. Okay, the green shape, okay, angular, okay, is greater compared to the rounded. Okay, and also the packing arrangement, okay, loose versus tight packing. Okay, definitely the tight packing have a higher coefficient of friction. Okay. So the magnitude of Fn increase the interlocking of two surfaces because the force push the imperfection together, making it harder for the block to slide. So this increase the friction force. Okay. So the magnitude of the Fn increase okay, if we increase the magnitude of the normal force, okay, increase the locking of the two surface because the force push the imperfection together, making it harder to the block to slide. Okay, so this is the same. Okay, okay, if we increase the Fn, so definitely the friction force will increase. Okay, so then it show a good agreement between the 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 normal force with the friction force. Okay. So increase if this increase. Okay, so I will just go fast for this example. Okay, so mechanical friction keep the block from sliding. Okay, and okay, this friction when we go deeply, okay, we can find that there are interaction between both surface of the block and also the surface of the failure plane. Okay, so okay, that interaction is due to the cohesions, okay, of the particles of the material. Okay? So the molecular cohesion between the grain also contribute to the material strength and keep the block from sliding. Okay, give me a second because I need to close the window because the outside is raining. Okay. Okay, moist sand has a strength. Okay, so this is example for when we want to build any structure on the sand. Okay, so we mix with a water. Okay, to easy to form or to remove this type of sand. Okay, so the strength is created by molecular force of attraction between sand, water, and air. Okay. So this example of calcite and silica, cement that bind mineral together in another form of molecular cohesion. So this is just an example, okay, to show that where there's some material have a good interaction. Okay. Okay. The stability of slope is analyzed by comparing the magnitude of the driving force to the resisting force. Okay. So we have here the FP, okay, which is the driving force, and also the Fn. Okay. So the ratio between this driving force and also the resisting force, okay, from there we can get the value for the factor safety. Okay. So the factor safety is a ratio between the resisting force and also the driving force. Okay, that's why in factor safety it doesn't have any units. Okay, because when force divide with force, which is the kilonewton over kilonewton, okay, there will be no value or units. So that's why factor safety is a value without any units or dimensionless. Okay. So from there, okay, from what we have discussed previously, okay, so the value or sorry the equations, okay, should be is W times cos theta and also plus the C, okay, the cohesions. Okay. For example, if we are using the total stress, so we rely on the C. Okay. If we are using the effective stress, so we can add on the phi value. Okay. So, then divide over W sine theta, which is the the driving force, okay, from the parallel force of the block to the failure plane. Okay. So at a low slope angle, theta Fp is small and Fn, and hence F are larger. Okay. So for example, if the theta is low, okay, so definitely the Fp will be reduced, okay, and it may contribute to a larger value of the Fn. Okay. So in that case, the factor safety is greater than 1. Okay. So in this case, and then for this case, at high slope angle, okay, the Fp is larger, okay, because the slope is high, okay, and the Fn and the Fn and hence Ff are smaller. Okay, the factor safety will be less than 1. So the factor safety, the slope fail if the factor safety is less than 1. Okay. So that is a simple explanation on the slope stability analysis. Okay. Okay. We take a break and then we may continue at 3. Okay. Because it almost 1 hour of lecture, then we take a break for a while. Okay. So because actually I want to stop the recording if I not stop, so it's very hard for me to upload for the 2 hours class. Okay. So that's why I break 1 hour, 1 hour. Okay. So we meet at 3. Okay.